Hello, I'm Rakshit Vishwanatha. I will be covering how Kalman filters work in this video. I'll go over how to use a Kalman filter, when to consider using a Kalman filter, and basically the whole process of how it's implemented. A couple of equations to show how the actual Kalman filter works. So after I talk about the Kalman filter, I will talk about sensors and sensor readings, basically how uncertainties in the sensor model and the mathematical model are kind of taken into account while using the Kalman filter. So once I cover the Kalman filter and the manner in which sensor readings are modeled, I will go on to the actual equations which describe how in each time step we update the values of the entity that's being estimated. And that's basically what the Kalman filter does. I mean, the Kalman filter tries to estimate something, and so with a simple equation for a one-dimensional use case, I will go over how the update equations come about and what happens in each timestamp. Starting with the Kalman filter, it's basically an estimator of a physical quantity. So when we say a physical quantity, it can be anything with respect to the system in consideration. So if we take a robotic arm, for example, we might want to estimate the angle that the arm is making with the horizontal. So in that case, the angle of the arm becomes the physical quantity that we're trying to estimate. So using the mathematical model along with the sensor that is there in the robotic arm, we try to estimate the actual angle of the arm. So we use the mathematical model along with the, say, IMU or the gyroscope or various other sensors from the robotic arm to estimate that angle. So in control systems in general, a lot of the times we club all of these physical quantities that we're trying to keep track of into a single variable. So in this case, that single variable x holds all the parameters that we're trying to keep track of. So in this case, it might be the position along the x-axis, the position along the y-axis, the velocity in the x-axis, the velocity in the y-axis. That may be the case for some system. Or it may be the angular velocity in the around the x-axis, the angular velocity around the y-axis, angular velocity around the z-axis. Those may be the physical quantities that we're trying to keep track of for a particular system. So all of these physical quantities form the states of the system, and they are all clubbed into a single vector, capital X. So the example that we will consider is a one-dimensional case, and we will be looking at the case where X is being consisted of the position P and the velocity V. So going to the next section, we'll head to the sensor readings part. So now let's consider a one-dimensional surface with a LiDAR sensor at one end, and we'll consider a ball, and let's assume this ball is able to move by itself randomly from 0 until capital D, this distance. So in this situation, we want to keep track of the position of the ball P, that is the position of the ball P from the sensor, and the velocity with which the ball is moving away or towards the sensor. So our state matrix or state vector becomes P and V, which is the position and velocity, and we club that into a vector, capital X. Now generally the manufacturer of the sensor also provides some uncertainty within which the sensor works, and this basically means that the readings that the sensor provides is not always certain, and they give a probability distribution to denote this likeliness of the reading being correct. So if the LiDAR sensor were to give a value, say 5, then they will say the value 5 is likely to be the case with a probability distribution of something. So in our case, let's assume the probability distribution is a normal distribution which has a mean of 0 and a variance of q. So in this case, the normal distribution, also called the Gaussian distribution, would be given by this formula, wherein it results in a curve such as this, which has the highest probability when we consider the mean, and it has a variance or a dispersal or uncertainty band called sigma. Now we take a look at all the equations for a one-dimensional Kalman filter problem. So as I explained earlier, we have the LiDAR sensor, we have the ball, and we're trying to estimate the position of the ball along with the velocity that the ball is moving with. So our state vector is x is equal to p and v. P is the position, v is the velocity. So when we talk about the Kalman filter, there are two main parts to it. One of them is the prediction part, and the second is the update part. The prediction is done using the mathematical model. So in our case, we'll have a math model which will tell us the position of the ball as each timestamp or each time step goes by. And using that model, which I've given here and I will explain, using that model, we try to predict what will happen in the next time step. The second part of the system will be the update part. In the update section, we actually use the sensor reading to try to get a better understanding of where the ball actually is. So using these two parts, the mathematical model predictions and the sensor reading or sensor measurement updates, we constantly keep updating the position of the ball and the velocity of the ball with every single time step as the time steps go by. Now looking at the mathematical model, here we assume that the ball always moves with a constant velocity. That is, that there is no acceleration. This means that if we are going from time step k minus 1 to k, the position of the ball at the new time step k will be equal to the position of the ball at the old time step p k minus 1 plus the velocity at that moment v k minus 1 into the time that actually goes by, which is delta t. And since we say it's a constant velocity system, vk is equal to vk minus 1. So the velocity at time step k is the same as the velocity at time step k minus 1. Now that we know the mathematical model, we can predict the state of the system at a time step k when we know the state of the system at a time step k minus 1. So that we denote by x of k given k minus 1. So what are we trying to do? We're trying to find the value of x at the time step k given we know the state at k minus 1. So the equation for that becomes xk k minus 1 is equal to fk x at k minus 1 given k minus 1 plus bk uk. Here f is called the state transition matrix and it takes the following form. The reason f takes the form 1 delta t 0 and 1 is because of the mathematical model that we had described earlier. So if we take a look at the matrix multiplication, we can see that pk is equal to 1 into pk minus 1 and delta t into vk minus 1, which is what we stated earlier. The position changes based on the previous position plus the velocity of the ball multiplied by the time step. And in the case of velocity, the next time step's velocity will remain the same as the previous time step's velocity. So that's what f becomes. F is the state transition matrix. So now that we know what f is, we can take a look at this equation again. So to predict the state of the system at the time step k, given we know the state of the system at time step k minus 1, we simply have to multiply f and k. We can actually ignore this b and u because u represents the input being given to the system, and in this case there's no real external input or no real driving factor that we consider for the ball. We just assume that it's moving freely by itself. So we can consider this to be 0, this term, and the effective equation becomes xk is equal to fk xk minus 1. Now, the first equation just went over how we updated the state of the system. However, we also have a corresponding probability distribution for the system. This probability distribution basically represents the certainty or the probability with which our mathematical model holds true. And it's given by another normal distribution, 0, q, where the mean is 0 and the variance or the standard deviation is q. So this also has to be updated in each time step. With each time step that we move, we not only have to update the state value, we also have to update the corresponding certainty or the corresponding probability with which we know that such an update occurs. And the equation for that is p at the time k given k minus 1 is equal to f at k into pk given k minus 1 into f transpose plus q. So by using these two equations, we will have updated the actual state of the system and the corresponding probability distribution or the corresponding certainty that the system exists in the state that we have predicted. So having completed our prediction step using the mathematical model, we now go to the sensor update step. So this is the theme with a Kalman filter. We predict the state of the system using the mathematical model, then we cross-check that with the readings we get from the sensor, and we cross-check this again using the mathematical model, and we cross-check the new mathematical model's output with sensor readings, and keep going back and forth, and we try to integrate the data we get from both the mathematical model and the sensor readings for the system. So the sensor update step has 4 main equations. The first one generates the error. The second calculates the Kalman filter matrix. And the next two do the update for the state vector and the corresponding probability distribution associated with that state vector. So in the error calculation step, zk represents the actual value that the sensor gives out or the sensor reads. Hk stands for the measurement function, and xk given k minus 1 is the value that we had predicted using the mathematical model. So what we're doing here is we find the error between the actual sensor reading and the predicted state from our mathematical model. Using this error and using the Kalman filter matrix, we then calculate our next state and our next time step probability distribution. So what is the value of h in this case? For a LiDAR, z, which is the actual measurement, only gives us the positional value of the object. It doesn't give us the velocity. So since we only get the position of the object from a LiDAR sensor, our H matrix should be such that from our state matrix or from our state vector, we are able to extract only the position. So for that reason, we put 1 and 0 so that when we multiply these two, we get only P. So our H matrix is 1, 0. Based on the sensor and based on the type and the number of outputs that the sensor gives out, the H matrix may vary from sensor to sensor. For the LiDAR, since only the position is given, we have to extract only the position section of the state vector. So now we know what H is, we know how to use this measurement function to transfer or to translate the entire state matrix into only the position value so that we can find the difference between the actual position and the estimated position. This gives us the error. This error is later used to update the state vector and the corresponding probability distribution. So now that we know what happens in one given time step, that is from k-1 to k, we have to do this entire process of predicting and updating. What happens in the next time step? Well, in the next time step, k just becomes k plus 1, which then becomes k plus 2. And for the sake of representation, k will be written as k minus 1 and k plus 1 will now become k. And when the time step goes ahead further, k plus 1 takes the value of k minus 1 and k plus 2 will take the value of k. And in this manner, the same equations given above can be implemented for each time step as it goes up one by one. So to recap the one-dimensional Kalman filter, we have a LiDAR sensor, we have a ball which moves by itself randomly. The ball moves with constant velocity v, and it moves randomly by itself without any external input or without any external forces. It's somehow able to move by itself. And we are trying to predict p and also v. So at the time step k minus 1, the ball's position is pk minus 1 and vk minus 1. And as we move to time step k from k minus 1, we apply the Kalman filter and we perform the two steps: the mathematical prediction step, mathematical model prediction step, and the sensor measurement update step. In this loop, the output of the prediction is then used for the update. And then for the next timestamp, the output of this update step is fed to the prediction step, which is then fed to the update step, and so on.